So we have two 30-minute talks back to back. These are the security talks. The best part of these talks is these tools that are going to be talked about are going to be available to you. So first is going to be Kostya from Soviet Russia. So he's come a long way to give this talk. So Kostya Serebryany, and one thing he said he likes to do is hike. I don't know about him, but I have been hiking up and down the stairs here at Google, so that's hiking enough. So with that, he is going to talk about AddressSanitizer, ThreadSanitizer, MemorySanitizer, dynamic testing tools for C++, and what we all like to call ASan, TSan, and MSan. So with that, here you go, Kostya.
Thank you, Tony, for introduction and for inviting me here, and thanks everyone for coming. So, dynamic testing tools for C++. I've heard this word only once in the previous talk and not at all in any other talks here. So raise your hands. Who is interested? Who cares about C++ code here? OK, thank you very much. Those who didn't raise their hands, wrong answer. You do actually care about C++. And here is why. So all the major browsers are written in C++. All the major operating systems are written in C++. All the major databases are written either in C or C++. Language interpreters like Perl, Python, whatever, are written in C or C++. And even if you are using Java, you are actually using one of the largest C++ code bases in the world. So this is why you actually all have to raise your hands. Let's continue. I will be talking about three different tools, ASan, TSan, and MSan. They're similar in spirit, but they find different bugs. Let's start from the first, which is now more than 2 years old. AddressSanitizer or ASan finds addressability bugs in C++. So these are buffer overflows, including stack, heap, and global buffer overflows. It also finds use after free bugs or dangling pointers, and some other interesting bugs as well. It is a part of two different compilers. This is now in release versions of both LLVM and GCC compilers. The compiler model instruments all loads and stores and does some tricky stuff with the stack and globals. The second part of the tool is the runtime library, which is basically a complete malloc replacement. It does memory allocation for the user, and it does some bookkeeping for to produce good error messages. So let's start from a few examples. For those of you who don't code or never coded in C or C++, C and C++ are not very safe languages. For example, if you have a buffer of 100 elements and you are accessing an element, say 101, no one will stop you. And this is like shooting your own leg. But AddressSanitizer will actually stop you. On this slide, you have a global buffer overflow, the smallest example I could write, 4 lines. All you need is to compile this test with a compiler with a special switch, and you will see a report which tells you everything about this bug. You will see a type of bug, it says global buffer overflow. You will see where it happens, and you will see the description of the buffer. A similar example with stack buffer overflow. The difference is that now it shows the stack variable, which is incorrectly accessed. The same for heap buffer overflows. Now it shows you where the allocated buffer has been allocated. And the most interesting and the most frequent actually in C++ is use after free bug. Since C++ is not garbage collected, users have to destroy their objects by themselves, and sometimes they actually access destroyed objects. This is happening pretty often. A few boring details about how it works and why it is actually very fast. we're playing tricks with the address space of the application process. We divide it in 3 parts. The upper part belongs to the application. Application does what it wants to do there. The lowest part is forbidden. It's unprotected. And the middle part belongs to the tool. It occupies 1/8 of the address space. And we store our own metadata in that in that piece of address space. So what do we store there? We need to note that any aligned 8 bytes of the application may have only 9 different states with regard to addressability. So n first bytes are good, where n is between 0 and 8, and 8 minus n bytes are bad. So since n is since 9 is less than 256, we can encode this number in 1 byte, and this is what we store in the shadow area. This slide shows what the compiler does with the memory accesses in the user program. So given a memory access, whether it's a read or write, we divide the address by 8 or shift it by 3. We load the shadow byte, and if it's not 0, we report an error. Very simple. This slide actually shows the instrumentation for 8-byte accesses. Smaller accesses are just slightly more expensive. They add like 3 arithmetic instructions. So this is a marketing slide, my favorite. First of all, for those of you who have heard about Valgrind, by the way, who have heard about Valgrind? Good. So if you know Valgrind, ASan is 10 times faster, sometimes 100 times faster, and it finds some of the bugs that Valgrind doesn't. The memory overhead of the tool is also tolerable, usually within 2 times. And the best part about the tool is that actually we have quite a few users, and those users are happy and they're finding bugs every day and as we speak. One of the major customers or users of the tool is Chrome. They have found many hundreds of bugs in the recent 1.5 years. The tool is used not just for tests, like we have, Chrome has continuous integration testing, as many previous speakers described, and ASan is used there. But Chrome security team is also doing fuzzing on 2,000 machines 24/7. Fuzzing means they're generating more or less random test inputs. Well, smartly random, I would say. And they throw these tests into the instrumented Chrome. This way they found really a lot of security bugs, which is even more entertaining from my point of view, is that external security researchers also do find Chrome bugs this way, and Google pays money for every such bug. So if anyone here is a security researcher, you're welcome to join the bounty hunt. Of course, Chrome is not our only user. We know that the tool found many bugs in Firefox, FreeType, in both compilers, in Perl, in MySQL, you name it. I don't know any project that has been extensively tested and which had no bugs detectable. Okay, let's go to the second tool. Data races are also well known to cause problems. One of the problems is flaky tests, which were discussed today a lot. Unfortunately, data races are also known for causing deaths in real life, so it is quite desirable to find them. Let's see what we have about the second tool. It is also using compile time instrumentation, and it is also a part of both compilers, both major open source compilers, LLVM and GCC. The major part of the tool is, again, runtime library, which is, again, a malloc replacement. It just has different algorithm inside. Let's see how it works and what it does. This is the simplest data race example I could write in C++. We have two threads that are concurrently accessing a single global variable. So no synchronization, no locking, nothing. And again, if you compile this test with a special switch, you will get a warning message, which will say that you have a data race. It will say which variable the race is happening on. It will show you two stack traces for the first memory access and for the second memory access. What does it do? What does the tool do with your program? It simply inserts function calls into your program before every memory access, and also at the function entry and function exit. Then we play the same exact tricks with the address space of the application. Well, very similar at least. We divide the address space into 4 parts. The first and the third part are protected. No one can touch them. The upper part belongs to the application. It's actually quite enough. It's like 32 terabytes of address space. You don't need more. And the second part belongs to the tool. We store our metadata there. How does this metadata look? We divide metadata or shadow into what we call cells. Every cell is an 8-byte word, which represents one access to a given memory location. It has thread ID. It has so-called epoch, which is a scalar clock. It has few bits for position and size, and 1 bit to indicate whether it was a read or a write access. And this 8-byte cell fully represents one memory access. There is no additional information anywhere. So for a given 8-byte word of the application, we have 4 shadow cells, which means that we have 5 times memory usage increase. Let's see what does this tool do with this shadow. Suppose we have this 8-byte word somewhere in the application, and the user code is accessing the first 2 bytes, writing something to the first 2 bytes. So we fill in the first cell, telling that this is thread 1, epoch 1, the range is from 0 to 2, and this is a write. Suppose later another thread is reading last 4 bytes. Again, we're filling another cell. Since there is no intersection between the memory ranges within the 8-byte word, there is no chance that this is a data race. Then a third read access comes. It is a read from the first 4 bytes. And now we have intersection between the memory ranges, between the first access and the third access. At least one of the accesses was a write. And now we need to figure out whether a data race is possible. So the answer to this question is the same as the answer to the question whether epoch 1 happens before epoch 3. I will not go into details here, but this is a very fast constant time operation, which basically involves a couple of memory accesses to the global state. It is well described in literature. So the one of the tricky parts of the tool is to how do we show the stack trace of the previous memory access. Once you have a data race, you can easily show the current stack trace, but not so easily the previous one. For this, we have per thread cyclic buffer of events. Events like function entry, function exit, and memory access. Each event takes 64 bits. And if the access happened too long ago, we may lose the data. But the buffer size is configurable, and the maximum size is enough for any data race we have seen. So when a data race actually happens, we replace this event buffer. This operation is slow, but it happens just once when you report a bug. So the overhead of this tool is significantly more than with the previous tool, but still quite tolerable, and to the best of our knowledge, it is the best in class among similar tools. So the slowdown is somewhere between 4 and 10 times, and the memory usage increase is 5 to 8 times. This tool already has quite a few trophies in Google. We started deploying this tool in the server side and have found many hundreds of bugs in our C++. What I didn't tell yet is that this tool also works for Go language. Raise your hands who knows about the Go language. Good. Now you all know about Go language, so raise your hands. The Go language is very interesting language which doesn't have buffer overflows, use after free, or anything like that in C++, but it still has data races. And I think the tool more or less found all of them in all of the existing Go code. There is quite a bit of it, but not as much as C++. Since our code is using some of the open source technologies, we also found races there. For example, one bug in OpenSSL was worth fixing, and there were a few benign races. I don't agree that they're benign, but okay. So we're just starting to deploy the tool with Chrome. We already found a few races, and I expect a steady flow of bugs in the future. Key advantages of this tool compared to all others. We believe that it's at least an order of magnitude faster than any other tool like this. And it natively supports atomic operations, which means that if your code does very low-level synchronization using atomics, we will still understand it. Most of the other tools don't. There are some limitations. This tool today only works on 64-bit Linux, so it will be a bit hard to port it to some mobile operating system. And it doesn't touch libraries or inline assembly or yeah, that's all. Okay, let's move to the third tool. The first two tools are already working and they're finding bugs 24/7. This tool is work in progress. We have not deployed it anywhere yet. The tool is called MemorySanitizer, and it finds uninitialized memory reads. Let me show you an example. And this is, again, a funny thing about the C++ language, which I, by the way, love. It's my favorite language. You can create a buffer. It will contain some garbage. You can read this garbage. You can use this garbage, and no one will ever complain. Well, the test may be flaky. The nuclear missile may go into wrong direction, but otherwise no one will notice, except for MSan. Of course, Valgrind also finds these bugs, but the speed of Valgrind doesn't allow you actually to use it as widely as we expect this tool to be used. Again, you compile the code with a special switch, and it will show you where the uninitialized access happened, and it will also show you where the memory was allocated, which was never initialized after. Okay, so how does it do? Surprisingly, it also uses shadow memory. This time it is 1-bit to 1-bit mapping. And every bit, if it is set, it means that the corresponding application bit is uninitialized or poisoned or whatever. Uninitialized memory is returned by malloc. So once you malloc the buffer, the whole buffer is poisoned. And uninitialized memory also comes from local stack objects. When you enter a function, if you have a local stack object, it starts from being poisoned. We have to propagate this poisoned bit through arithmetic operations. I'll show you why later. And once a constant value is written to a memory location, the corresponding shadow is unpoisoned, meaning that we have initialized it. So this is again the direct mapping, which makes the tool extremely fast. If you want to compute the shadow corresponding to an application address, you just subtract some large constant from it. Or you actually unset one of the bits in the address. This is the same operation here. One of the problems of many tools that find uninitialized reads is that they report what they think are bugs very early, and what I think are false positives. Here is a simple example. Suppose you have a struct in C language which has a 1-byte object following a 4-byte object. So who knows what is the size of this struct? No one? 8 bytes, correctly. So this struct is 8 bytes because there is a hole due to alignment. You have 1-byte object, then 3 bytes of nothing, and then a 4-byte object. So when you allocate this object, it is all uninitialized. Then you initialize x and y. It gets unpoisoned, but the hole itself is still poisoned. And if you are doing some things like memcopy with this object, you are copying uninitialized bytes. And some of the tools are reporting bug at this point, which makes the tool unusable. Valgrind is one of the few tools that don't do this, and our tool doesn't do this either. So we have to propagate the shadow bits through some of the arithmetic operations like addition, bitwise AND, and so forth. Enough about this. We also need to know who actually allocated the poisoned memory. Like you have 2 calls to malloc, then you add the results, putting it into some third value, and then you figure out that this value is uninitialized. You need to know which malloc is guilty. And MemorySanitizer does it by using yet another part of address space. It stores their locations of the it stores IDs of the allocation site, like malloc or stack frame. The MemorySanitizer has very moderate overhead. It's like 3 times slower than the native run, and it uses 2 times more memory. If you want to get origins, it's twice worse, but still quite tolerable. The tricky part about this tool, which is not about the first 2 tools, this tool actually has to see all the memory accesses in the program. Otherwise, it will report false positives. So we need to compile everything: libc, libc++, all the libraries that the program depends on. And this is actually quite doable in a wide range of cases. Like we can handle LLVM itself. For larger programs like Chrome, for example, it's not that easy. Chrome depends on 77 shared libraries on Linux. So we have to do some dirty tricks to instrument the libraries at runtime. As I said, we didn't deploy MSan anywhere significantly, but it already has some good trophies. We tried it on a proprietary console applications, more than 1 million lines of code of C++. It was not tested by Valgrind previously, we found 20 plus unique bugs in just 2 hours. We then tested it with Valgrind. Valgrind finds the same, but in more than 24 hours. And MSan gives better reports for stack memory. And we have found a few bugs elsewhere. So to summarize what I just told, we have 3 tools for C++ and one of them also for Go language. ASan, as we believe, is a must-use for everyone who is developing or testing C++ or C programs. Today it works on Linux, OS X, Chrome OS, and Android, on x86, on ARM, and a little bit on PowerPC. Work in progress is iOS, Windows, BSD clones, etc. And this is a part of 2 major open source compilers, Clang and GCC. TSan is a must-use if you have threads, because then you most likely have data races. Today it works only on x86 Linux, and it is also a part of 2 major open source compilers. MSan is a work in progress tool which finds uses of uninitialized data. Stay tuned if you're interested. At this point, I will be happy to take questions. Thank you.
Great. Thank you. So I learned 2 really important things here. One, Kostya loves C++ because it keeps him employed. And the second thing is, if you don't use his tools, you are shooting yourself in your leg. So use the tools. Okay. I'm going to give you one pre-announcement, then we're going to take a question. We are going to have drinks after GTAC today. We're going to do the same thing we did yesterday about shuttling everybody up. And then please do stay for Claudio's talk after the questions here. It's going to be about XSS, which affects everybody here. So with that, please, first question.
Alec Monroe. To bring things back to, I think, where the languages most of us work with, I know, say, Python, for example, has shed skin and Cython that can compile down to C++. And while generally when programming Python, we don't worry about address, wrong address, or memory sanitization, but we do worry about thread issues. We do have data races there. And I'm just wondering if there's been any work to look into whether you could use something like ThreadSanitizer to actually test Python code for data races.
My knowledge about Python is quite limited, but I know that there is something called global Python lock or something like this, sure. Which means that Python is actually single-threaded. If you try to remove that global Python lock, then you're in big trouble, and TSan is your friend. But other than that, you probably don't need it.
Okay, thanks for
Thank you.
Thanks for the question. We have one up here on the moderator. It says, does AddressSanitizer catch accesses outside the current buffer, but within another valid buffer?
Yeah, that's a good question. So we may have 2 buffers, one which was expected to be accessed, and one which is actually accessed because the index was so far away that it jumped to another buffer. And there is a red zone between them. So if you are accessing like 1 kilobyte outside of the buffer, we will not detect it, yes. But the most frequent accesses are within the first 16 or 32 bytes. And this is what we catch reliably.
Yeah, great. All right, Kostya, thank you.
Thank you.
Thank you.